So good morning. Let us start today's class. Yesterday we are discussing about the first unit. In the first unit we are almost discussing about the types of reactions and examples for the types of reactions, law of mass actions, then how to write the rate for chemical reactions, different type of chemical reactions. In CRE1 we will be only using the first one, whereas 2, 3, 4 and 5 we will be using in CRE2. So in CRE1 we will only use based on the volume of the fluid. So how to write the rates for different reactants and products. You can write the rate based on the consumption of A or consumption of B, or if there is one more reactant, even you can write for that also. So here the negative tells it is reactant and positive tells it is for product. So this is the relationship. The rate of disappearance divided by the stoichiometric coefficient should be equal to the rate of disappearance of another compound divided by its stoichiometric coefficient is equal to the rate of formation of the product divided by its stoichiometric coefficient. One example I gave, 2A plus B gives 3R. So here the stoichiometric coefficient of A is 2. The stoichiometric coefficient of B is 1. Stoichiometric coefficient of R is 3. So we can write the rate of disappearance of A divided by 2, that is its stoichiometric coefficient, is equal to rate of disappearance of B divided by its stoichiometric coefficient is equal to rate of disappearance of R divided by its stoichiometric coefficient. And from this, if you want any two chemicals, you can relate like that. That is A with R, you can relate, right? Or B with R, anything, right? Or A with B. How many times of A is getting consumed to that of how many times of B is getting consumed, right? So here I stopped yesterday, I think. So today we'll start. Not only we wrote this particular thing, a rate as minus 1 by V into dNA by dt is nothing but the moles of A disappeared per unit volume of the fluid per unit time. This rate, it depends on a lot of factors. On what factors this rate disappeared, right? That is what we will be seeing today. Factors affecting the rate of a reaction. One, the nature of the reactants and the products. Based on the nature of the reactant, your rate will change. Not only that, concentration of the reactants. If the concentration of the reactant is high, your rate will be high because it is directly proportional. If the concentration of the reactant is less, then the rate also will be less, because we already saw here this, the concentration Na by V, we are going for a constant volume. One second, sorry. Sorry, some small disturbance in my throat. Yeah, here minus 1 by RA, you are assuming it is constant volume. Volume constant in the sense, volume of the fluid inside the reactor is constant. Then we can write Na by V as Ca. So from this equation, we know that the rate is directly proportional to concentration, the change in the concentration. The more the concentration, more will be the rate. The less the concentration, less will be the rate, right? That is what here I am giving. The concentration of the reactant, not only the concentration, the pressure and temperature plays a very important role. The temperature plays a very important role. As the temperature increases, your rate will change. In fact, the rate is very sensitive to temperature. Even a small change in temperature or even one small degree rise in temperature, your rate will shoot up by more than 100%, 200% like that. The other one is the pressure of a system. So concentration and pressure, you can write the rate in terms of its concentration, or you can write the rate in terms of its pressures also, especially if there is a gas phase system. Instead of concentrations, we will write in terms of the pressures. That we will see how to write in terms of the pressures. Not only that, the rate will depend on the factors is the catalyst, especially in CRE1, we won't get these three, but in CRE1 we get only these. But the rate depends on the catalyst, the type of a catalyst, then the surface area of the reactant. If there is a solid surface, solid reactant, how much of the surface is available for the reaction. Not only that, there will be the rate of heat transfer and a mass transfer. This heat and mass transfer plays a very important role in the rate. That all we will study in CRE2. In CRE1, we are discussing about homogeneous reactions. Only these three we'll see. In fact, even the temperature we won't see. Temperature we'll see only in the unit number 4. That is temperature dependent terms. How when there is a temperature change, non-isothermal. How you have to include that into picture. The rest of the thing we'll be seeing in the CRE2. So in CRE1, we will be discussing only these three, right? So how to write the rate for any homogeneous systems? Minus RA. Minus RA is nothing but the rate. What is rate? Rate of a reaction. It is nothing but the moles of A disappeared. If you are writing the rate for the reactant, then moles of A disappeared to that of unit volume of the fluid per unit time. That is the rate. So that rate is a function of, one is temperature dependent term, the other one is concentration dependent term. There are two terms here. One is temperature dependent term and concentration dependent term. So generally we assume constant temperature. Therefore, you won't take this temperature dependent term into picture. You'll write only the concentration dependent term. So to explain more about it, we'll write the first rate and then we'll discuss more about it. Now let us consider a reaction A gives R. Let us consider a reaction A gives R. I think 54 are there. Am I audible, ma? All the people? Or you are there?
Yes.
Okay. 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 Because in between I need to check whether my connection is correct or. So if you consider a reaction A is giving R, let some K is there. Let some this is some K, that is the rate constant. So A is giving R, A is the reactant and R is the A is the reactant, R is the product. K, let it be some constant, rate constant we call. So minus RA, if you want to write the rate of disappearance of A, minus RA is, you can write your rate as a function of temperature dependent term and concentration dependent term. So this K, rate constant we call, this K belongs to the temperature dependent term and the concentration term is Ca. Ca power alpha. Alpha because alpha tells it is the order of a reaction. Since only one molecule of A is there, alpha will be 1. If there is 2A, then it will be square. If there is 3A, then it will be cube, right? So minus RA is K into Ca power alpha. This is how you have to write the rate. Rate in the sense minus RA is the temperature dependent term into the concentration dependent term. This power you'll use that tells you it is the order of a reaction. If the order, it depends on this stoichiometric coefficient. If there is a 2, then you will put 2. That's why we put alpha. So here K is the temperature dependent term, and if the constant temperature is there, then K will be K. But K is a strong function of temperature. A small change in what do you call K temperature, this K will change. The K will change according to Arrhenius equation. I don't know whether you come across that. Minus RA is, you can write K as K naught exponential E by RT into Ca power alpha. So this entire term is nothing but the temperature term. This Ca is nothing but the concentration term. So what is this K naught? K naught is the pre-exponential factor. E is the activation energy. R is the gas constant. T is the temperature in Kelvin. So this is how you will write the rate. But since K is a strong function of temperature, is an exponential function of temperature, as long as the time is constant, that is temperature is constant, you can assume that K is constant. But if the temperature is increasing, then you cannot take K as constant. Right? So you have to express this in terms of this and then do some integral things. So where K naught exponential E by RT is the temperature dependent term, Ca power alpha is the concentration dependent term, Ea is the activation energy. Activation energy is the minimum energy required for the molecule to take part in the reaction. Alpha is the order of a reaction with respect to A. It can be order, can be one or first order, second order, or third order. Based on that, alpha will change. So this is a very important expression, how to write the rate. Rate is a function of temperature dependent term and concentration dependent term. So the concentration dependent term of the rate equation. So here we are assuming the temperature is constant. For the first 3 units, we are assuming the temperature is constant. Only the concentration is changing. So when the concentration is changing, how you can write the rates? That is what we will be seeing here. The temperature concentration dependent term of a rate equation. The temperature of the system should be maintained constant because we are assuming it is isothermal. There can be a different types of reactions, especially constant temperature, but constant concentration dependent term for a different kinds of reactions you have to write. Either it is single or multiple reactions. Single reaction is A is giving R. Multiple reactions is a series reaction or a parallel reactions. We have to know what is elementary reaction and a non-elementary reaction. The other one is molecularity and order. These three we are very important, very much important. Each one is a 2 marks question. We'll see what is elementary and non-elementary now. What is the single and multiple reactions, right? First single and multiple reaction. Now single reaction is like this. A is giving some product. Whereas multiple reactions can be a series. A is giving R is giving S, where R may be a desired component. But if you're not taking enough steps, the R desired component may turn to undesired component yes. Or sometimes yes will become a desired component. It depends on the condition of the what do you call the product, right? The next one is a parallel reaction. Parallel reaction is two products are competing to form, but the reactant is same. A is giving R and A is giving S. This kind of reactions are called as competitive reactant because there will be a competition for the formation of R and S, whereas only one particular product is desirable, whereas there may be another undesirable reaction. So we need to suppress the undesirable reaction so that only the desirable reaction will come. So there will be competition, how you are taking that into picture and doing the design. That is what we'll be studying in parallel reaction. Either the parallel reaction can be like this, or there can be a side-by-side reactions. A is giving R, B is giving S. So in the two things, the same thing. This is side by side. So not much of competition is there because A is giving R, B is giving S, some other component. There can be a more complicated system like a parallel and series combinations also will come. A plus B is giving R. Again, this component which is being reacted or formed, it reacts with again B. that is the one more reactant to give you another product, it is S. So if you see this kind of reactions, this is parallel with respect to B, parallel with respect to B. The reaction is parallel with respect to B because here you can see this is parallel reaction. From the same reactant, you are getting two different products. And there can be a series reaction like this. A is giving R is giving B. So A is giving R, again A is giving S because R is reacting with this to give you S. So there will be a series and parallel combination. If there is a combination like this, it will be very complicated, and to write the rate, it becomes very difficult. Right? So 1 second, I'll just. Yeah, right. More complicated systems, parallel and series combinations will come. Right. Next, we have to discuss about elementary and non-elementary reaction. Very important 2 marks question will come. Now, when we call the reaction is elementary and when we call the reaction is non-elementary. Now, if you assume there is a single reaction in the sense some reactant is giving you product. There is no parallel or series combination. So A plus B is giving R. This is a kind of single reaction. If this reaction is elementary, then you can write the rate as minus RA is equal. So you have to write both. So if you are writing this equation and the rate is like this, then you see what is the corresponding coefficient of the reactant A? It is 1. The corresponding coefficient of reactant B is 1. So the power to which the Ca is raised is 1 and this is 1. So if whatever coefficients are having here, stoichiometric coefficients, if they are appearing in the rate expression as the powers, then this kind of reaction is called elementary reaction. This kind of reaction is called as elementary reaction. So here, whatever stoichiometric coefficient is there, that should reflect in the powers. That is alpha. That is what I just told here, alpha, right? So that alpha is a power 1 now because the stoichiometric coefficient here, the stoichiometric coefficient here. This kind of, if this stoichiometric coefficients is in correspondence with this particular rate expression, then we call it as elementary reaction. So elementary reaction, we can tell the order. Order is nothing but the sum of the powers of the concentration. This is sum 1 and this is sum 1. This is what do you call power 1 and this is power 1. So 1 plus 1 gives 2. So order of this reaction is 2. So for an elementary reaction, you can tell the order directly looking at this particular expression. Only for the elementary reaction, we can tell the order. Lot of reactions are non-elementary. We cannot tell the order just by looking at this particular expression. You have to do some experiment, find out the order. Only from the experimental results will be finding out the order. But if the reaction is a elementary reaction, we can find out the order just by looking at the coefficients. So this is a one example of non-elementary reaction. H2 plus Br2 gives 2HBr. That is hydrogen plus bromine gives HBr, hydrogen bromide. This is a non-elementary reaction. If it is an elementary, then we can write minus RH. This is disappearance of H2 is K times concentration of H2 and concentration of Br2. Right? But this is a non-elementary reaction. The order, if you can write you get an order like this. Now you can see HBr. We are writing the order for the formation of HBr. HBr is the product, so that is why you are not putting negative. Is K1 H2Br2 power 1 by 2. So H coefficient is 1 here. Br coefficient is 1, but you are getting in the order as half divided by K2 plus concentration of HBr divided by concentration of Br2. This square bracket tells you concentration. Either you can write CH2 CBr2 like that, or you can put a square brackets. The concentration you can put like this, CH2 CBr2, or you can put the square bracket, this is H2 into Br. This is the general way to write the concentration, especially in terms of the rate, not this. Okay. So now if you see here, if it is an elementary reaction, this is 1 and this is 1, the order should be 2. But here if you see, this is order 1 and this is order half, it is 1.5. Again, there is some denominator. So this particular rate expression is not correspond to this particular equation. That is why we call this as non-elementary reaction. For a non-elementary reactions, how we have to write the rate? How we get this rate like this? That is what is the next topic. For a non-elementary reactions, you cannot tell the rate order. Whereas for an elementary reactions, you can tell the order. So you have to write this particular non-elementary reactions like a series of reactions, especially initiation, propagation, termination steps you have to do. You have to write this non-elementary reactions as a series of elementary reactions and then write the rates and then club the rates to give you this particular final thing. So for a final non-elementary reactions, to find the rate, you have to divide this equation as a series of steps, like a series reaction, right? So let us see what is molecularity and order. Yeah, any doubt here? Any doubt here? You understood what I want to talk there? Any doubt? Yeah, please put it. Or you want me to go to the next slide? I will go. Yeah, some of you can give the feedback. One of you. Am I any doubt?
No, sir.
Shall I go for the next slide? Yeah, I'll go. Then molecularity and order of a reaction. What is this molecularity and order? Again, for elementary reaction only, we can tell the molecularity and order. So consider the reaction type AA plus BB gives RR, where small a is the stoichiometric coefficient of reactant A, and small b is the stoichiometric coefficient of reactant B, and small r is the stoichiometric coefficient of reactant R. So the molecularity of a reaction is nothing but A plus B. This particular thing. This is 1 and this is 1. Therefore, A plus B will give you the molecularity. Now, what is order? Order, if the reaction is an elementary, then we can write minus Ra as K into Ca power A, because the stoichiometric coefficient, and Cb power B. So here A is the 8th order with respect to A. This reaction is 8th order with respect to A, because this particular thing, and Bth order with respect to B. So order of a reaction is nothing but the sum of the powers, A plus B. Now you can ask me, for an elementary reaction, generally your molecularity and order will be same. Correct? Because this is A plus B and this is also A plus B. For a non-elementary reactions like this, now this is 1 and this is 1. Therefore, molecularity is 2 here, but the order you cannot tell, because this is 1.5 in the numerator, denominator. Again, this is no order, and this is also there will be no order, because okay, it gets cancelled out, right? So this may be around 1.5, around 1.5, 1.6 like that. So earlier itself I told order can be a fraction. Understand? For a elementary reaction, now you see here the molecularity is 1 plus 1 2. Order is also 2 because 1 plus 1 2. For a general elementary reactions, your molecularity and order is same. Whereas for a non-elementary reactions, the order and the molecularity may be different. Definitely there will be some difference, right? That is what this slide gives you. Now we'll see one important thing. Yeah, one important thing is rate constant. What is this K? What is this K? K is a rate constant. Earlier itself I told this K is a rate constant. How to write the rate constant? I already told. K is a strong function of temperature. So you have to write an Arrhenius equation. Is already you studied in school chemistry. K is K naught exponential E by RT. That is what we will write here. For a homogeneous chemical reaction, especially the dimensions of rate constant is very important. The dimensions of the rate constant is for an nth order reaction. For an nth order reaction, K will have a unit of time power minus 1, concentration power 1 minus n. Concentration power 1 minus n. This is the general order of a reaction. General order of a reaction. Now, if n is the order, now if a first order is there, if the reaction is a first order, then what will happen to the K unit? Now, K unit you can see here. K unit. K is concentration power 1 minus n into time power minus 1. So n is 1. Therefore, K is equal to concentration power 1 minus 1 into time power minus 1. Therefore, 1 minus 1 is 0. Concentration power 0 is 1. Therefore, K is time inverse. So the unit for K, especially for a first order reaction, will be that is per time, right? So how much, this is a very important thing. So second inverse, hour inverse, like that it will come. This is only for first order. Now, if the order is 2, then what will have the unit of K? K will have different units, though it is called as a rate constant. This rate constant will have different unit based on the order of a reaction. So K, if it is a second order reaction, like A plus B is giving you some product. So this is 1, this is 1. So second order reaction, then K will have a unit of, now K is concentration power 1 minus n is 2 into time power minus 1. So 1 minus 2 is minus 1. So K is concentration power minus 1, time power minus 1. That is nothing but 1 by concentration into time. So concentration will have a unit of meter cube per liter or centimeter cube per liter. Then time will have a unit of per second or per hour or whatever it is. Therefore, concentration 1 by concentration unit is meter cube, how many in per liter, into time is hours. So we can write liters per meter cube hour. This is the general unit for K if it is second order, right? So it can be liters or whatever you want to change, milliliters or even whatever you want to change, you can change, right? Sorry. This is meters into liters. Both are unit, same liters, right? This is what is that? Moles. Sorry, mole per liter because concentration, right? Moles per liter. So this will be moles, right? Moles. Liter can be converted to meter cube. Sorry, I missed it. This meter cube and liter is interconverted, right? 1 meter cube is 1000 liters. So concentration unit is mole per liter or mole per meter cube, right? So it will be liters per mole per hour, right? So like that, if there is a zero order, what will happen if the reaction is zero order? This becomes 0. Therefore, this will K will have a unit of concentration power 1 time power minus 1. Therefore, K will have a unit of moles per mole per liter into R, right? Mole per liter into hour. It is just the reverse to this. Liter per mole. This will be mole per liter. So this is for zero order. This is for first order. This is for second order. You can write for any order, right? You can write for any order. Shall I go for the next slide, ma? Any doubt? This is a very important bit. What is the order? Especially it is time power minus 1, concentration power 1 minus n. N is the order of a reaction. Now we'll see how we can write the rate. What do you call rate for a non-elementary reaction? Kinetic models for non-elementary reactions. Now you see here, there is a reaction A2 plus B2 gives 2AB. So this, if it is an elementary reaction, if this is an elementary reaction, you can write your rate minus R based on A2, that is the reactant, is K times, this is let it be K, concentration of A2 into concentration of B2. So this is 1, this is 1, the order will be 2. But if this is non-elementary, then you cannot write the rate like this. You have to find out the rate. You have to find out the rate. For finding the rate, you have to split this equation into a series of elementary steps. How we can split, that is what I am giving here. First, let us think that A2 is forming some intermediate. Let A star is the intermediate or free radical or whatever you name. Free radical or polar molecules, transition complex, anything, whatever you want, you think. So we assume this, there is a chain reaction which is happening to form this AB complex or AB product. So in that chain reaction, we will see that A2 is forming some intermediate A star. That A star intermediate is highly unstable. It is reacting with another molecule, that is B, to give you some AB intermediate again and some intermediate B star. Again, this A star, one A star is going here. There are two A stars here. One A star is forming this. Another A star plus this one more component is giving you AB. So if you because you are assuming this is a irreversible reaction, but when you are writing as a series of steps, you are assuming it is a reversible reaction. Either it can form this or this. So total 6 reactions are there, because this is 2, this is 2, this is 2. And if you club all the reactant and all the product, you are going to get this particular thing. So you are splitting this equation, non-elementary reaction, as a series of elementary steps. And you have to write your rate expression based on what is available, that is A2, B2 and AB. We don't want this intermediates. We don't know what is this intermediates. So when you write the rates for this, if you are assuming the elementary reaction here, and if you write the rates, your rates will be in the form of B star, A star, which we don't know. We have to eliminate. Once we eliminate the equations and club all the equations, then we can get the rate for this particular thing. This is how you have to go for searching the mechanism. Here I am splitting like this. If I am splitting like this, and if you calculate the rate expression, if the rate expression corresponds to this particular thing, then it is a success. Otherwise, you have to search one more mechanism. One more mechanism that we will see, right? So types of intermediates forms can be a free radical, ion and polar substances, molecules can form, transition complex can form, chain reactions, non-chain reactions. The next slides will just give what are these free radicals and all, right? So that you can read, just you can see here free radicals, free atoms or larger fragments of stable molecules that contains more than one or more unpaired electrons is called free radicals. So these are highly unstable reactive free radicals. Then iron and a polar substance, electrically charged atoms, molecules or fragments, right? So transition complexes, these are very highly unstable. This is what we are assuming. This is transition complex, which is highly unstable. It forms and then again it reacts with one more highly unstable to give you the product. So you can see further collisions returns to the molecule in the normal state. Such unstable forms are called as transition complexes. There will be two more things, non-chain reactions and chain reactions. What is this non-chain? Non-chain reactions will happen like this. Reactants are giving you intermediates. That intermediates are giving you products. So this kind of reactions mechanism is called as non-chain reaction mechanism. So reactant is giving you some highly unstable intermediates. That intermediates are forming to give you products. There can be a chain reaction mechanisms, especially here. This is a chain reaction mechanism. If there is a chain reaction mechanism, what will happen? The reactant is forming an intermediate, because chain reactions will have 3 steps: initiation, propagation and termination. Whereas non-chain reactions will have only 2 steps. This is the initiation and this is the termination. There won't be any propagation step. Whereas chain reactions will have 3 steps. So reactant is giving you some intermediate. That intermediate reacts with the reactant to give you one more intermediate and the product. Again, this intermediate again gives you the product. So this is the propagation step, this is the initiation step, and this is the termination step. So in chain reactions, we'll have 3 steps. That is what I showed you here. This is a chain reaction. Reactant is forming intermediates. Intermediates is reacting to give you product and some intermediate. Again, that intermediates are giving you the product. So this kind of mechanism is called as chain mechanism. The other one is unchained mechanism, where it is a reactant is giving you intermediate. That intermediate is giving you the product. There won't be any propagation step. So in the propagation step, intermediate is acting like a catalyst, especially in the chain reactions. This intermediate will act like a catalyst to form the products, right? So now we'll see some mechanisms. I'll give you some problem so that we can see that mechanisms, right? So let me go back to this one more thing I'm having. Now, please, all of you, write the notes. Take this particular problem. I'll put this in terms of one more. This. One second. I'll just. But yeah, now this is there is a reaction, or you can use the same problem. I'll just show you. So this is the irreversible reaction. 2A plus B gives A to B. Has been studied kinetically, and the rate of formation of the product is found to be correlated by the following relation. So there is a reaction like this, and he is writing the formation of A to B. A to B is the product. He is giving you the rate. A to B is 0.72, Ca power square, Cb power 1, that is the concentration, by 1 plus 2 concentration of A. So in the problem is asking you what mechanism suggests by this rate expression. If the chemistry of the reaction suggests that intermediate consists of an association of reactant molecule. This is the question. So in the question, what is giving you? He is giving you the equation. He is giving you the rate. So he is asking you what mechanism you choose in such a way that if you write the rate for this, especially the product, you get this kind of rate. So we'll see that now this is the reaction which we have to do. We assume this is a non-chain mechanism. So reactant is forming some intermediate. Intermediate is again reacting with the to give you the product, right? So let us see that. So let us, it is a non-elementary reaction as the order and the stoichiometric coefficient are different, because if it is order is same, this is 2 and this is 1, therefore the order should be 3. But if you see the rate here, the order is 2, the order is 1, but there is again denominator term also. So we know from this particular thing it is a non-elementary reaction. So for the non-elementary reaction, it's asking you how to find out this rate, what mechanism we have to devise. So that is what is giving. It is a non-elementary reaction as the order and the stoichiometric coefficients are not the same. So we should devise only 2 steps. Let us devise 2 steps. What are the 2 steps? Non-chain mechanism. Let us assume 2A is giving you A2 star, and A2 star plus B is giving you A to B. Am I right? This is how I'm taking. This is how I'm taking now, right? This is how I will be taking. So 2-step mechanism, some intermediate is formed, that intermediate is disappeared to give you the product. So this I'm writing as a irreversible reaction. The forward reaction, let it be K1. The back reaction, let it be K2. The again, second reaction K3 and K4. So what we did is, this particular equation, this particular one equation, we are splitting into 4 elementary reactions. This is a highly non-elementary reaction. We are splitting into 4 elementary reactions. Yeah, please take a notes along with me and then write. Otherwise, you lose what I'm talking. Now we will write the rate of formation, overall rate of formation of A to B. Rate of formation, because he is asking you in the problem the rate of formation of the product. The rate of formation of the product. So he is asking you the rate based on formation of the product. So let us write the overall rate of formation. What is the overall rate of the formation? So you are splitting the equation as 4 different equations. Wherever A to B is there, that you have to write. So the rate of formation of A to B is nothing but R A to B. Rate of formation alone I am writing. Where A to B is formed, in this reaction there is no A to B formed or disappeared. In this reaction there is one A to B formed in the K3. Am I right? So the rate of disappearance or the rate of formation of A to B is nothing but K3. K3 it is forming into the concentration, this particular thing. So wherever this equation is coming, this arrow mark, from that side you have to put this K3 into this. If you are writing this, K4 into this, because it is the reactant and this is the product. So always we will write your rate based on this particular thing. So rate of formation of R A to B is nothing but, here it is formed K3 into concentration of A to star into concentration of B. That is what I am writing here. Now how it is A to B is disappeared. How A to B is disappeared, again you see. In the K4 step, A to B is disappeared to give you this. So how to write now? Disappearance is nothing but minus R A to B is equal to K4. How it is being disappeared? The reactant is this particular thing. Earlier the reactant is this. That is why you wrote here. But here you are writing the disappearance of this. Therefore, the reactant is this. That is why K4 into A2B. Correct. What is the net rate? Because we want the net rate of formation of the product, right? That is what he's asking. Formation of product. Net rate is nothing but how much is being formed minus how much it is being disappeared. It is just like you are getting some 5 rupees and spending 2 rupees. How much net gain you are having? It is 5 minus 2. The same way here. This much is the formation. This much is the disappearance. So we want net rate is nothing but the formation minus the disappearance. So K3 A2 star B minus K4 A2 star. The concentration term I am putting as a square bracket. You can use the same thing. Now you see the rate of formation R A to B. E writing in terms of K3 we know, B concentration we know, this concentration we know, but we don't know A2 star because this is an intermediate. You have to eliminate this A2 star. If you want to eliminate this A2 star, you have to write again the rate of formation and disappearance of A2 star, because A2 star is an unstable component. In your reaction, there is no A2 star. In this reaction, there is no A2 star. You are assuming there is some A2 star which is being formed, and now you have to eliminate that A2 star. That is what we will do now. So A2 star is an unmeasurable quantity. We need to please put some numbers for it, so that we'll be substituting in the reactions. So first reaction is this. K3 is this particular thing minus this is RA to B because the formation. A2 is unmeasurable. So unmeasurable quantity you have to write in terms of measurables. How to write now? Rate of formation of A2 star. Where the A2 star is formed, can anyone tell where the A2 star is formed? There are 4 reactions here. How many reactions A2 star is formed? Yeah, one of you please tell. A2 star, where it is formed? In K1 reaction, A2 star is formed because 2A is given to A2 star. But in reaction 2, A2 star is disappeared. Again K3, A2 star is being disappeared. Again K4, A2 star is being formed. Am I right? So where is the formation? Formation is nothing but K1 step and K4 step. So we are seeing the formation alone. Therefore, we can add K1 plus K4. Am I right? So K1, what is that now? K1 Ca power whole square, because there is 2, because this is all the what do you call elementary reactions. So K, yeah, you can see here A2 star is K1 A square because two components are there, divided by half, because you know that if you want to compare the rate with this particular then this rate divided by its stoichiometric coefficient divided by this rate divided by its stoichiometric coefficient. So if you are writing that, the stoichiometric coefficient will be half, right? So that is what you will be writing here. K1 A square divided by 2. This is for the first one. What is for the fourth one? What is for the fourth one? K4 A to B, because this is where it is formed, disappeared to form this particular thing. So K4 A to B. K4 A to B. So let it, you put as this is second reaction. This is first. This is the overall formation. This is only the formation for the intermediate. Like that, we have to write the rate of disappearance of the intermediate, where the disappearance K2 step it is being disappeared, and K3 step also it is being disappeared. So how we will write K2 step? K2 into A2 star plus K3 into this particular thing, A2 star plus B, because the equation is going like this. So wherever this particular thing towards the left you have to write. Since the equation is starting here, you are writing this particular thing. Am I right? So the rate of disappearance, the rate of formation, disappearance is K2 A2 star plus K3 A2 star B. This is third reaction. Yeah. Any problem till now? Only these three steps are difficult. Afterwards, it is just adding one to the other thing. Any doubt you ask? I'll just clarify here. Emma? Some of you can give. Yamini, you're there?
Yes,
Yamini? Any doubt, ma?
Yes, no doubt.
You're the class rep, right? Yeah.
Yes,
Sir?
Because I
Sir?
I remembered your name because my daughter name is Yamini. So okay, good. Any doubt, ma, here? No, right?
Sir?
No, sir.
Any doubt now? Till now? Writing these two steps? Formation and disappearance of the intermediate. Now what we have to do? We have to
Sir, could you explain the K1 A square by 2 step, sir? How we got it from the
yes,
2A to A2?
that's what I'm trying. Yeah, now this is right. So if you write the rate is K1 into CA square, this you know, right? Divided by half you are putting because you are trying to compare whenever there is a coefficient here, you are trying to compare how much is the disappearance to how much is the appearance of this particular thing. Then what will happen? This particular thing divided by its stoichiometric coefficient. That is what I showed you here.
Yes, sir.
I'll just, by stoichiometric coefficient. If you want to compare the rates, rate of disappearance of this with appearance of this or something, then you have to divide by its stoichiometric coefficients. That is why we put this. That is why we put this by stoichiometric coefficient. It is nothing but 2. Correct? Any doubt?
Okay, sir.
If there is 3, then it will be divided by 3. Yeah, good doubt, because I expected some of you to ask that. Yeah, any other? Any other? Any other doubt? Can I go ahead with the next one? Only this writing 3 steps is important. Rest of the thing is all just manipulating these 3 equations so that you get the final form. Can I go for next? Now this intermediate, you write the formation.
A square?
A square because this is 2 molecules. You are writing this is elementary reaction. Elementary reaction, your rate corresponds to this stoichiometric coefficient. The stoichiometric coefficient is 2. That is why you are putting 2. A square.
So we have to divide by stoichiometric.
Yes. Because you are writing formation and disappearance. So to compare, you write 2.
Okay.
So now here you are writing the formation of A2 star and disappearance. But this A2 star we cannot see or we cannot measure. What we have to do at an equilibrium, we assume that the rate of formation of A2 star is equal to the rate of formation of rate of disappearance of A2 star. So if you equate 2 and 3, then what will happen? This A2 star will go. Remember, right? If you equate 2 and 3, because at an equilibrium, we assume that the rate of formation of A2 star is equal to the rate of disappearance of A2 star. Then if you equate 2 and 3, this equation with this, then what will happen? K1 by 2 A square plus K4 A2B is K2 A2 star plus K3 A2 star B. A2 star is common. You can take it outside. That's what I'm writing. A2 star is K2 plus K3 B. And this is same. We want K2 star. From this equation, A2 star is nothing but K1 A square. Sorry, the student missed this square. A square plus K4 A2B divided by K2 plus K3 into B. Now we got A2. This is the fourth one. A2 star. Now this you put in the first equation. What is the first equation? First equation is this. This A2 star, which is unmeasurable, we found out how much it is. A2 star, here it is in measurables. A we can measure, what do you call concentration of A. A2B we can measure. K1 rate constant, K4 rate constant, K2 rate constant, K3 rate constant, and B also we can measure. So you are writing unmeasurable quantity in terms of measurables now. Now substitute this A2 in for 1, then what will happen? R to B, K to B into A2 star. A2 star you have to substitute the entire one minus K4 A to B. So you have to cross multiply and then take numerator and denominator. You do it, then you get the final form. You have to make some assumptions, then you will get the final form. Now you see, I am cross multiplying here. This K3 star I am multiplying with both the thing. So if I multiply first one, K3 K1 by 2, A, B, square is there. She missed here, but here square is there. Square is there, right? Square is there. That same square you tell me. Plus 2 times, because here again she is cross multiplying because there is 2 here. So 2 times K4 into K3B minus again K4 A2B into K2 plus K3B into this divided by this. So if you split this particular thing, what will happen now? You see K1 K3 B A square by 2, right? Plus 2 K4 K3 A to B minus K4 K2 A to B minus K3 K4 B into this. This is negative quantity and this is positive quantity. It gets cancelled out. So you are left with numerator 2 terms and denominator 2 terms. So if you divide, so K1 K2 by 2 B A square minus K4 K2 A to B divided by K2 K3 B. But in the expression, what he asked you is, in the expression, based on your expressions, you is asking you denominator 1 plus. So what you have to do, you are getting some K3 there. You are getting some K2 here. Here. You are getting some K2 here. So divide this term by K2. Then what will happen? It will come as 1. You are trying to manipulate in such a way that you are trying to get the expression what is giving you. So divide by K2, then what will happen? If you divide by K2, then what will happen here? K1, K2 by K2 it will be there. Then here K3 by K2 will be there. Here K4, K2 by K2 will become. So K2, K2 get cancelled out. And if you put K1, K3 by 2 K2 is 0.72. Why? Because again you are putting, because since he is asking you it is 0.72, he is having a coefficient of 0.72 and K3 by K4 is 2. If you put that substitute, because these are all constants, you can do whatever you want there. Then what will happen? Now you see K1 K2 by 2 K2 minus K4 by 1 plus K3 by K2 B. This is almost corresponding to the whatever he gave. Here, if you make it as 0.72 and this is 1, K3, K4 if you make as 2, then this is what he is giving you. 0.72 A square B plus 1 plus 2B. That is what he gave you. But this extra term is there. What is this extra term? K4 A to B. What is K4 A to B? K4 equation is, what is K4? K4 equation is the disappearance of A to B. But in the problem, he is asking you the formation of A to B. So what we do is, if you want to eliminate that particular thing, because there is no term here, only one term, there is no second term in the numerator, you are getting K4. So what we do is, K4 is the disappearance. So we assume that K3, the rate at forward reaction is much larger than the backward reaction. Then what will happen? Only the formation will be taken. The disappearance can be neglected. So K3 is very small, very greater than K4, or K4 is very smaller than K3. If you make that assumption, then what will happen is, now, yeah, K4 is much smaller than K3, then it can be considered as 0. So this term will vanish. Therefore, 0.72 A square B divided by 1 plus 2B you get. Is this the same expression what he is asking? Again, go back. See the denominator. You are getting the same expression, but the denominator is 2A should come. But we got as 2B. You see here. is in the problem is asking you it is 2A, 2Ca, that is concentration of A. But what we got is B. So that means that what we assumption, that is A2 star is being formed, is wrong. So we have to devise one more mechanism in such a way that you get A. That is what the rate expression does not satisfy with the given expression, hence the mechanism is wrong. So we will search one more mechanism. A plus B is giving you AB star, and AB star plus A is giving you A to B. Again, 4 reactions. So AB star is the intermediate. Earlier you put A2 star is the intermediate. Now we are putting AB star is the intermediate. Now again do the same thing. Now you will get it, right? Yeah, copy down this and then try to do, and we'll meet in the next class, right? Already time is over. Yeah, Yamini or Guru, you are there? Yamini or Guru?
Yes, sir.
Anyone?
Yeah.
54 people are there. Please give the attendance. Yeah, it is difficult to take the attendance. Yes. I know. Try to send the attendance. Okay. So you can share yourself so that you send the attendance. Okay. Any doubt, ma, in the class? It's already 5 minutes late. So hope everyone understood.
Sir, will we be,
yeah, tell me.
so will we be able to access this PDF on LMS, sir, just to look through it again?
Yes, ma. I'll, if you want, I'll store in LMS, but it takes more space, yes, and all. But the notes, everything I am putting. If you want, you can copy, download the notes. You want the videos, then I'll try to download. You have to download it and then upload. It takes, because it is
not the
almost
videos,
1
sir.
hour.
The PDF that we just now went through, I wanted to know if we could look through the derivation.
This PDF.
Yes,
yeah, I'll put it. No problem. This is student notes.
Okay.
Already I took last year. I took from that student. I asked her to scan it and then send. Otherwise, I have to start writing on the board. It becomes a very, what you call, time consuming, because there will be too many derivations which becomes. Yeah, I'll put this. No problem. I'll put in the LMS. You can see in my LMS page, already I put a lesson plan. These are the 2 books, which are Octave Levenspiel and Gavane. And I put the lecture notes and pre-class video also I put. You want me to put this notes also, I'll put. Today I'll put. Okay? Okay, ma'am?
Okay. Thank you.
Okay. You can see all the people are in LMS. So I'll stop here because it's already lunch time. Thank you for joining. If any doubt is there, you can use the WhatsApp group and send me your doubts. Then in the next class or in between, whenever you want, I'll just clarify it. Okay. Thank you. I'll stop the recording now.